And thanks to the organizers for having this session and for having me here presenting this work. These are some of my collaborators here. This is work that we have been doing the last few years with these people here. So I don't have a lot of time for this talk. So I think this talk I want to give three main takeaway ideas. I'm going to start right directly with the first one that actually ties very well with what Alini was presenting. That actually, I think that if you ask me, and of course we can debate this a little bit later, but the stellar coronal mass ejections probably are not as common as the flare frequencies that we observe seem to indicate, right? And this is related with this kind of idea that in the sun, we know that flares and coronal mass ejections are related phenomena. Big flares on the sun, usually most of the time, very high association rates with CMEs. And their big flares, usually all of them trigger coronal mass ejection. So we know this. And one thing that you need to remember that is energetically, so coronal mass ejections are probably as important as flares, maybe even more important. So of course, the immediate question for the stellar people is like, well, what happens in more active stars? Because we see them flaring all the time and with flare energies and frequencies that are much larger than solar. So a bunch of people in the past already did this question, and some of the works that have tried to answer this are listed here. But I would argue that, I mean, it was the paper by Jeremy Drake back in 2013, the first one that tried to put some numbers into this and realize that what were the consequences of extrapolating what we know from the sun to the stars, okay? And some of these consequences are written here that a saturated star, like in the saturated regime, would put a lot of mass loss in the form of CMEs, and we lose a lot of energy in the form of CMEs. So the conclusion of that work is that you cannot extrapolate this all the way. So this is one thing that at the end of the talk, I hope this stays. So what is the possible solution? This is what Alini presented a little bit. Is like, maybe coronal mass ejections are being suppressed by the magnetic field of these stars. And this is actually a solar idea, right? In the sun, sometimes you have these very big active regions that have very strong magnetic fields. They generate a lot of flares, but they don't generate a bunch of CMEs. So they're so-called flare-rich CME poor. So we follow Jingchuan advice. So we actually took a solar mature validated model, okay, and tried to apply these two stars. So we took advantage of the work done by Mang Jing and collaborators using Awesome and the Eagle model that was presented earlier, simulating 3D CME simulations on the sun, but we modified this in a way that we just suddenly make the large-scale dipole of the sun stronger, okay? And in this case, yes, as you can see in this animation, what should have been a very massive and powerful CME, it didn't go anywhere, okay? So the perturbed plasma remained there, confined the corona. The same eruption occurring in the nominal sun will look something like this. So a big eruption, fast speed, a very strong and energetic CME. So the thing that we saw is that the mass of these things were kind of akin to each other between the sun and the stars, regardless of whether or not they were confined or escaping. But the important part was that all the CMEs were slowed down by the presence of the large-scale field to the extent of sometimes actually be completely stopped. So one thing that I want to make that maybe is clear here is that these predictions are actually consistent with our best candidate events, okay? And this is actually something that I think is important for us that do models. We need to go back at the data all the time and see what we're doing. You should also have a look at this work that was done very recently that also considered this problem from a different perspective in the form of maybe the presence of these large-scale magnetic fields actually prevents the entire eruption from happening from the instability point of view. So I recommend this paper there. So until very recently, and not for lack of trying, we had no definitive detections of stellar CME. There's a bunch of papers here, and actually looking at some of these references, and many people have looked for them, okay? Back in 2019, Sophia Mosho, we tried to do a compilation of historical candidates. There's a very nice review by Martin Leitzinger in 2022 that I recommend. But this is kind of a little bit how the things look. This is a CME mass, CME kinetic energy. These are all candidate events, but I think as Rachel says, that most of them are just weird looking flares, right? So that's it. So I think these are just some data here, but basically the extrapolations are the red lines, okay? So the first thing I want to make your attention is that the masses, you know, more or less for the solar extrapolation, whereas the kinetic energies of these candidates are significantly lower by several orders of magnitude, okay? There are, I think, two very strong candidate events for CMEs, which is the event reported by Constanza Giroffi and the one that we have heard a lot about today at EKDRA by Namekata-san and collaborators, that they will fall in this plot here. Again, similar kind of situation. We can discuss whether or not this is related with the prominence eruption or the CME or what are we looking here. But the situation is that we are just basically trying to get some more data that we can improve our models. I don't know how I'm doing on time, so I'll try to rush a little bit. The second part that I wanted to say is that the phenomenology and observational signals of stellar CME might be different from what you see on the sun, okay? And that actually comes when we have applied these models to other regimes, for instance, the one that you expect for M-dwarfs. So this is a dynamo simulation produced by Rakesh Yadav a few years ago, tailored to Proxima Centauri that generates cycles. It has, you know, all the bells and whistles and whatnot. We use it to drive coronal mass ejection simulation, and the idea was to study what happens when they are driven in these magnetized environments that we expect for M-dwarfs, okay? So we did this to explore a little bit this magnetic confinement spectrum in which you can have CMEs that just, you know, get launched and have a lot of energy when the magnetic field of the star is relatively weak, so the CME goes away. Then you increase the magnetic field of the star a little bit, and then the CME, you know, it has a harder time, but manages to escape. And then in cases in which, you know, the magnetic field is very strong, and then the CME doesn't go anywhere, okay? So this is not a sharp transition, it's probably like a more smooth transition, okay? So, and then of course, we did a lot of synthesis analysis. So we simulated synthetic observables to see how these things look like when you observe it within the eyes of like solar observations. So this is emulating AIA images. So this is a still images of different snapshots of the simulation. And I have here just a quick recap of what we see in a way. Like what we see is that when we launch these events, there's this response of the corona that actually triggers a lot of reactions in different wave bands. So we actually, for instance, if you see the yellow middle panel, we see these dimming signatures that you typically observe in solar events, okay? So this is an escaping CME, but we also see these flare-like profiles that are triggered by magnetic compression, okay? So this is in the case of an escaping CME. And I think one of the things that actually can resolve this apparent paradox that Alini was talking about is that actually, if you look at the middle panel again, this is a fully confined event, and we still see coronal dimming events, okay? You can get coronal dimming events even when the mass doesn't go anywhere, okay? Because remember, we cannot be putting all the mass that the flare distributions imply, because probably you will get into trouble with the mass loss and the energy requirements, okay? So this is an event that is fully confined. The plasma doesn't go anywhere, actually falls back into a star resembling what we call some sort of a coronal rain. And I think this is actually very interesting because the observations in this very nice paper by Tom reporting this behavior of this constant redshift observed in this relatively warm or hotter transition region lines of EKDRA, precisely the same star in which we have seen this, probably these eruptions, okay? It's not that CMEs are not happening, it's just that there are a lot of conditions that maybe are harder conditions to overcome in the stellar regime. Okay, the last part of this talk, because I don't know if I'm already running out of time. The last thing is that I wanna say is this is more recent work that we did. So actually CMEs could affect the stellar angular momentum loss in non-trivial ways, okay? And this is actually work that was carried out by Yu Hu, also known as Yuki, because pronouncing his name is difficult, but Yuki has done a lot of work simulating coronal mass ejections in a young sun-like star, kind of star, in which I have spent a lot of time, but I don't want to talk about it right now. But basically, this is kind of where the simulated events lie when compared with the solar events, okay? So we're simulating things that are a little bit towards the high energy and high mass end of the solar spectrum. And the idea is to analyze what happens with the angular momentum loss. So this is a plot that you saw already. So basically, we trace the evolution of the CME, but what we see is that this actually perturbs the Alfvén surface. And maybe you're not very familiar with this concept. This is actually a theoretical kind of structure, but it exists, that is actually very useful because we use it to be able to quantify what is the influence the wind is having on the rotational evolution of the star, because this serves as the lever arm in which the magnetic torque is being applied to the star. Because if you're changing this surface, what this means is that you're changing the torque that is being applied, and then it would change the angular momentum evolution. So we try to quantify this with a bunch of numerical simulations. So you can see here, maybe you can read the RAR, it stands for active region, and the FR, it stands for flux rope. We had a dynamo-generated magnetic field map for our star because we wanted to have some small-scale structure where to anchor our coronal mass ejections. And we simulated a bunch of them, and then we followed the prescription in the more general way to calculate the angular momentum loss, which is given by this equation, and I recommend the appendix of this paper by Alini, where she does the derivation of it. And we're using the most general form because some of the simplifications that are typically done in the steady state, they are not going to apply in the time-dependent situation that you're going to have when you have this CME, massive CME going out and perturbing the Alfvén surface and changing all the parameters, changing the velocity, the magnetic field, and all of these parameters that are here. So one thing that I want to draw your attention is this is mass loss. The angular momentum loss. It's just positive because we wanted to, get rid of the minus sign. But remember that everything that is positive in this plot is the mass loss, the angular momentum loss that the star is having because of the wind. But I want to draw your attention to these two cases here in which the black line, which is the combination of all the terms, actually goes to negative values. So what this means is that in some cases, for some parameters which were not very trivial, and we actually don't know yet exactly what are the conditions, but in some cases, this angular momentum loss changes sign. So what this means is actually that the CMEs are not, the star is not slowing faster as you would expect for just launching CME. It's actually the opposite, okay? And this is what I wanted to convey here, that these CMEs, because of the structure and the way they interact with the magnetic field, the way they change the Alfvén surface, they can actually have these non-trivial responses in the way they would affect the angular momentum. So, okay, that's it. These are the same 3 points that I had before. And just maybe one last thing that I wanted to say here is that we want to understand these stellar CMEs and the phenomena associated like SCPs and the impact of exoplanets and all of this. We need to go to realistic CME rates. We cannot continue to extrapolate the solar values because this is going to take us into dangerous places. Thank you very much.
So we take 3 questions that will open up for general discussion.
This one, yes? Oh, I'm sorry. You mean that when we have a confined CME, the reason why we see dimming. This is what you wanted to know, yes? Yeah, yes, exactly. And I think the other thing we see is that sometimes you can't have displacement of the material. So things are being evacuated, but those materials, they don't go beyond, right? So they will just get launched, but they will fall back into the star somewhere else. So here we see it, for instance, in other latitudes, they get redirected back very far from the launching site, basically. Yeah. Yeah, I mean, oh yeah. So Moira's asking, so where is the angular momentum coming from when the CMEs are launched? So what we thought about a lot about this, and I think the reason is because all of these 4 terms, right? So in many cases, and especially when you're only considering the steady state, at least the first 2 terms cancel out. But in this case, because the CME arrives to the Alfvén surface, and actually you have a very different angle between the magnetic field and the velocity field, which this doesn't happen. I think it is actually coming from magnetic tension. This is my assumption, but I'm not 100% sure of this answer. One thing that we saw is that when the CME arrives, the Alfvén surface shrinks. So it's this analogy of, the lever arm shrinking, so you will get this increase of rotation. But that's not the only reason, because that term does not dominate over the others. So when we did the analysis term by term, this is not the dominant term. The dominant term is the magnetic field directionality one. Yeah. Yeah, so if I understood the question, if what we think is happening is that maybe yes, so the question is that if basically the CME spectrum, right? So if there are going to be less smaller events and perhaps once in a while very big ones in a similar fashion as maybe we think that sometimes the sun, for instance, can have super flares. I think that's probably a way of seeing things. I think I believe that this magnetic confinement process is occurring at all scales. That's actually, I could reverse this question in the sense that why we don't only observe the range of masses and kinetic energies we observe on the sun, right? So why we don't observe even weaker events, right? I think the confinement occurs on completely different ranges, and it will just allow certain windows of masses and kinetic energies to exist. There will be some events that are more likely to happen than others, but this is just simply a condition that right now in the current sun is not so important, or at least not in the large scale, but is important in the small scale. But I think for other stars in which the small scale and the large scale are comparable, which is what we see from observations, then it will become even a more prominent situation. So.
And we'll move on to like the general discussion for 15 or so minutes before the break. So maybe what's best is if you put your hand up, I can bring the microphone to you. Oh, sorry. Okay, sure. Two online questions.
Yeah. So before the discussion, there are two questions online, not yet answered. First question is to Jun Chang and from Emery Isik, I think. And so his question is about the kappa 130 field extrapolation that is used for CME simulation. If the active regions are significantly smaller in size than the length scales resolved by ZDI inversion, which seem to be rather low degree, what would be the implications of the dynamics of the CME in the simulation? It would be interesting to see a CME from artificial magnetograms.
Yeah, I agree with that comment. It will be interesting to see. Yeah.
Okay. And the second question is to Alain Bidotto. So why do you think that open field regions are only around poles?
This is a result of the stellar wind modeling. So when the stellar wind is combined with the magnetic topology coming from ZDI maps. So not necessarily only around the poles, you might have a more complex topology that you would have open field line regions. In this case, it happened to be at the poles.
Any question?
I would like to address the final point on this view graph about exoplanet habitability and photochemistry models. There's been a number of papers on the point that CMEs can essentially photodissociate nitrogen oxide and nitrogen oxide molecules, leading to the destruction of ozone, which would have an effect on the habitability at the surface of an exoplanet. I think that Alain's paper was really relevant to this question because planets typically are close to the rotational equator of a star, since they're formed out of the same cloud. And if the CMEs are primarily at the rotational pole or near the rotational pole of a star, and they are directional, then they will most often miss the planets. Therefore, any estimate of the effect of CMEs on photochemistry of exoplanet atmospheres and habitability really should take this into account, that most of the CMEs are going to miss the planets.
I think I think that first. So a bunch of hands came up in response to what we were saying. Who was first?
Now, I'm not an expert on this at all, but I don't think the magnetic fields like pole and the rotational pole of a star have to necessarily be aligned. I thought for like, is it AUMIC or something? It's very much in the plane of where the planets would be. So even if they were high latitude, it's the magnetic pole rather than the rotational pole.
Yeah, and I just wanted to give more bad news, I guess. So if you launch a CME within an open magnetic field line region, these are the regions where the wind is traveling faster, right? Like in the coronal holes that we see on the sun. And what happens is that in order for generate the shocks, the CME needs to go faster than the local speed in the co-moving frame with the wind. And it needs to overcome a faster stellar wind, and it needs to overcome a much larger Alphen speed. So those two conditions are gonna, put very, very high, requirements for the speed of the CME to induce a strong shock where your particles are gonna be accelerated. So this is another thing that I didn't talk here, but since in our simulations we're predicting slower CME speeds, we're also predicting that generating shocks is harder for CMEs around very magnetically active stars, because not only the CMEs are slower, but the Alphen speed in the corona are higher. So that's it.
So as a direct counterpoint to what Julian just said, in the sun, we just had this example, back in mid-May of a sunspot group that released flare after flare after flare. And what happened was the second, third, and fourth flares were much faster than the preliminary one because the space had been cleared. And you had shocks because they literally piled up on top of each other. And Julian, I understand that you don't want us to be using the solar model, but this is the example we have.
Well, thank you for bringing up the recent event in the last month. So I want to use that point to back up Julian's point, because during that 10 days in the last month, we have about 150 flares above M class. So M and X flares during 10 days of period, but only less than 20 of those are associated with CMEs. So it's very clear that a lot of flares are not associated with CMEs, even in the solar cases. And these flares are confined. And a good news is that in operation, we were able to just use X-ray flux and the hardness of the spectra to kind of predict which flares can be associated with CME and which will be confined. So this is another example of how we can use the solar model to apply to the stellar environment, since we have so many X-ray observation for the stellar flares. And also we do have the spectral resolution to tell the X-ray hardness for the stellar flares. So essentially we can use this method and tell which stellar flares can be associated with CMEs. And also another point that's not only the hardness, but also the relative intensity of the flares. For example, in the last month, most of even the background X-ray intensity is above the M class classification. So any of the small bumps are marked as an M class flare. That's why you see 150. So another important factor is your peak X-ray flux versus your background X-ray flux. So this can be obtained in the stellar observation as well. So yeah, that's the.
Hi, CSAR, CFA. I was struck. Would I be correct in thinking that you might be able to detect failed CMEs by a flare, which is followed with a time delay an enhancement in the transition region lines due to coronal rain falling back down?
Here is an additional question from Zoom from hello, sorry. And the question is, pre-CME evolution requires a lot of a closed field. Anyone could have any comments on that? The pre-CME evolution required a lot of closed field lines. What do you mean? Yeah. Okay.
Yeah, so I think you need reconnections to have flares, so it happens more at close field line.
What do I have to talk? This? I think, I'm not sure if I understand what the person probably means is this is why it's a little bit dangerous just to put in a flux rope in the background because in reality, these flux ropes or filaments, they are stable for a long time before they erupt, days to weeks, which means, and that's what this person probably means, there is always a closed field around it, always. Otherwise, you cannot have an equilibrium, right? And that's what I meant before, that these are closed fields on the local scale of the active regions, okay? What is above is a different story, okay? There may be high arching, still closed fields, or there may be open fields, but you have always these kind of fields. And so in order to get the CME, you have to overcome these fields, okay? So again, I caution you just to put in a flux rope, which is not stabilized, not in equilibrium, nothing. It has no weight and exploding, and then making this kind of conclusions. And the other thing I would like to say is that because you guys always talk about the confinement by the field, that this is not the only way to get a confined flare on the sun. Okay, so one thing is you have an eruption and then the field above it is so strong and stops it. But there are other ways to get confined flares. For example, you have QSLs, quasi-separatlix layers around these flux ropes. And even if the flux rope doesn't erupt at all, you may perturb this system or loops are pushed together. And if you have strong magnetic fields, you will get a relatively strong flare. So you do not, and it doesn't matter what is above, okay? So that's just in terms of these ideas of what confines. So that's not the only way. In other words, there's only one way to get the CME. You need something to erupt and it has to go out. But there are more than one way to get a flare without the CME.
Hi, I'm Shubhajit from NASA Goddard. So I have a question related to Epidorodus flare, and there the coronal dimming is around 13 hours or so, and it is more than the rotation period. So if it was like 6-7 hours, or and another thing also, the polar, there is active polar region. So first point is, if there is 6-7 hours, if we get next time the coronal dimming, then will that say that it is not a polar event or a polar event? So this is one part. Another thing, I was thinking, like, there is the corona is optically thin. So if it is not like, and the coronal loops are much bigger in, so when the star is rotating, the only thing is happening like when it will be eclipse, when it will be behind the photosphere. Otherwise, there will be some transparency also. So maybe it is not necessarily at the corona, at the polar region. Maybe since it is, the loop is bigger and it is not behind, exactly behind. So so it can be more hours or so. Yeah, I want to know your thoughts. Thank you.
So we can certainly brainstorm more this afterwards, but my understanding, I don't know, I don't know what to say if it's the duration is smaller than the rotation period. I don't know, I can't tell you where, if it's possible to be at the pole, if it's possible, I think it could be anywhere. But the fact that the duration was longer than the rotation period is a very strong indication that the event is always in view to us. So that's why the inclination of the star, we know the inclination of the star. So this is why we think it is coming from this around it's not at the pole, it's a high latitude, maybe something about 60 degrees.
Question, like if like loop is bigger, so when the star is rotating, maybe part of the loop is behind, means so the coronal, maybe you can see it, and until it is behind the photosphere, it is invisible. So it is, that's why it is the 13-hour. It is 13-hour can be justified because coronal is optically thin.
No, I understand, but I would expect them to be, oh, okay, I see what you mean. Yeah. These are X-ray, and this was EUV observations, yeah.
Means it will be eclipsed when exactly it is behind the because corona is of the it is eclipsed by
I think
corona is
yeah, I think there is a simple geometric calculation that we can do, yeah.
So 13 hours from a 12-hour period is possible without being a polar event. That's what I'm.
Okay, yeah, good, thank you.
So that's past. So I think we're going to break now, but come back here after the posters for the next half of the session. And I was told that all the swag is here, so you have to go to reception to pick up your swag. But let's thank all the speakers again. And come back at 4 o'clock.